Okay, so for 8 and 9, number 8, what we want to do is calculate the erosion index, which is the two layers we just made, and then we have to bring in the slope 30, which we had made in the previous step. So what I need to do is just bring in that, let's see, there's a few layers that I might just want to clean up here a little bit, so I'm going to remove what I don't need. It's just going to be messy. It's going to get rid of the geology layer, the problem part 1. So I just want it down to the canopy effect and the infiltration effect. I'll get rid of this canopy raster. And then I can go back to my set number 1. I guess I removed that before, but I want the slope 30. And remember, slope is going to be values of 0 slope at flat to 90 degrees at a sheer cliff. That was a layer that I had made in my chapter 11 set. We should see that slope 30 meters as a GIS layer. So remember this one from last time. So we have those 3 layers. Let's see what equation she wants us to use for that. So she just wants us to multiply those 3 layers together. If we take a look at the numeric values here, slope ranges from 0 to 90, and then these 2 layers are both under 1, and so it's going to essentially take the slopes and it's going to keep reducing them based on the slope is the most important variable, but if it happens to be a steep slope where there's high infiltration, it brings it down, or if it's a steep slope and there's canopy cover, it brings it down, or if there's some combination of both of those that are high, it brings it down even more. So, but if again, the canopy effect one only, or the infiltration only goes up to 0.5, so at a minimum, it's going to take these values in half and maybe even further down depending on what canopy effect is there. So think of that through mathematically. In the end, what we'd expect then are values, none of the values being over 90 for sure. They're not going to go over 45 really. If we see something over 45, we'll think something maybe has not gone right. So it's a pretty simple step. Step 8 as it is a really, really easy one. All we have to do is go to the geoprocessing, go to raster calculator again, launch that tool again. We just need to take these 3 layers all times each other. So we take the slope times the infiltration effect and then times the canopy effect. And I don't know if she gave us a suggested name. Essentially, this is erosion index. Okay, and so let's take a look at how those values come out. It's going to be 30 by 30 meter pixel cells, and this is pretty promising. Let's see, the numeric values are ranging here from about 0 to 21, which is reasonable compared to what we were thinking. The highest values could have been as much as 90. They weren't. There was very few places that were actually a sheer cliff, so a lot of those numbers are lower anyways. And then you're already taking them down by half just because of the one effect, and then you're taking them further with the canopy effect. So to get a high value of 21 makes sense. This is what that map looks like. And in this case, you have higher erosion potential in any areas that are the bright colors on here, and then lower for the dark colors. I think a black and white doesn't do erosion very much. It doesn't really speak to erosion very much. I kind of like for this a scale that goes from like greens to yellows to reds, just as a way to show like green means low slope. These are pretty good areas for erosion. Yellow means in between, and red means high potential for erosion. This might just show a little bit better those areas that are particularly vulnerable for erosion, something like that, and areas that are very low susceptibility across those 3 factors. All right, so that's really your answer for number 8, as it is. 8, calculate it, and then capture the map. And what I'd like to have you do is capture the map with this legend at least in there as well. You could just take off these other layers. Okay, number 9, then what she wants you to do is a tool that's so helpful, and that is if you have a raster and you have some kind of a GIS layer that shows various regions within your map, it'll summarize all those raster cells underneath those regions. And so this could be applied to all kinds of things. If you have population density and zip codes, population density as a raster and zip codes as a vector layer. You can summarize all the population density in each zip code. In this case, we're just going to be summarizing how much erosion potential there is per watersheds. And so for number 9, we need to find a GIS layer of watersheds, which I suspect will be just in that South Dakota layer. We need to go back to that. SPC, C, our class, the Sturgis geodatabase, and then in the features, let's see if there's a watershed layer. There's actually 2 of them, watershed 2B and 2C. Let's see what's the difference here. I'm guessing that, she doesn't really specify it, does she? Determine the mean erosion index. Oh, she says in 2C, watershed 2C. So I'm going to go ahead and remove. Do you see what the difference between these 2 layers? It's just one of them is more finely dissected watersheds. This is the big watersheds as they are, the big named rivers, and then this is the watersheds broken up into finer pieces. And so she wants the one broken up into finer pieces. I'm just going to go ahead and remove that layer and keep the C. So these are our regions. It's going to summarize all those values underneath this. The tool that I like to use for this, if we go to geoprocessing, it's a set of tools called Summarize Zones. But I like to do this one called Summarize Zones to Table, and then I'll do a table join to bring that standalone table back to the watersheds. I find that just it works better with the tools. Zonal statistics as table is what we want to do. It's this zonal statistics as table is the tool I like. The input raster is going to be that shows the zones. This could be a feature or a raster of the zones. We want that to be our watersheds. The field that we want to use for this is some unique value for each of the watersheds. I want to look at the attribute table to see what would make the most sense here. There's one called watershed ID, and there's one that's just like a numeric value that seems to be sequentially going up. I'm just going to use the ID that just seems to be, unless there's some repeats in there, each one will have a unique value. Sometimes there will be a name that you could use for this. You know, this is Walnut Creek, or this one's Clear Creek or whatever, but it looks like they don't have anything like that, so I'll use the one that ends in ID. The input raster we want for this is our erosion index. And then it's going to make a new GIS layer that's called Zonal Statistics of Watershed 2C, which is a pretty good name for it. It's going to run all statistics, but let's just take a quick look at what she's actually looking for. Determine the mean erosion index. So if you don't want to run all the statistics, you could just run the mean. And then I'll go ahead. So what's going to happen is it's going to add a standalone table down here where there's going to be one value for each of these unique ID values, and then a mean erosion index for each one. Again, we shouldn't see any mean erosion index higher than 22 and lower than 0. We'll think something has gone wrong if we see that it's not within that range. Remember, a standalone table, you can right-click and go to open that table. We'll take a look. Here it is. Those are the unique values. There's a count of how many raster cells were in each one of those watersheds. And then I'm going to sort this descending. You should see small values, but nothing going below 0. In fact, that's what we see. And then I'll sort it descending. And we see values that are as high as 7.6, which again seems reasonable. It doesn't go over 20 for sure, and so that seems reasonable. Okay, so what we're going to do, so we can, I wonder if we can answer the question just based on what we've done so far. Let's just see how this is phrased. Determine the mean erosion index for each one and capture a map. So we need to make a map with those means. So in order to put this back together, we need to do a table join where we're using the watershed ID as the join field, join the standalone table back to the watershed. So I'm going to go to right-click on my destination layer, the watersheds, and then go to Joins and Relates, add a join. The feature that we want to use for this is the watershed ID. It's going to join to the destination is going to be our watershed's C2 layer. The table we want to join from is our zonal statistics, and we want to use that watershed ID. Keep all features. I'm going to go ahead and click OK. We'll know this worked if we see when we open back up the watersheds layer that there is going to now be a mean column in here. Let's set the zoom, scroll over. Oh yeah, it's hard to do with this zoom on. And it's the last column there is the mean, so that seemed to have worked. Now we'll use the symbology for this layer. Instead of single symbol, we'll use graduated colors. Instead of area, we're going to use the mean. That's the mean erosion index. Again, those values are ranging from just above 0 to 7.6 across the watershed. And it makes sense, right? You guys see the places that are the reds on here are turning out to be the dark blues on here. The areas that are, these areas here that are all green, vast areas of green are coming out to be those low values on this watershed. So in the end, you would capture a map that is the legend plus that particular map here. Again, the idea behind this is that for each of these watersheds, you would be characterizing them in terms of the potential for erosion across those three variables. All right, so that is how we would work through. And again, I took it off officially off the assignment to do question number 10 on the assignment.